Dear fellow scholars, this is a new episode with a special guest. Today we are going to find out what happens if we feed an AI the most mysterious book in the world and ask it to translate it. What makes this book so special? Well, first of all, just look at it. It looks beautiful with its hand-drawn illustrations and diagrams. It has been suggested that this might be a kind of herbal with recipes and such. But then there is this one problem. While the illustrations look biologically realistic, all the text in the book seems to be a jumble of letters that make absolutely no sense. But wait, you might say, Google can translate any book you want. So let's just ask Google. And dear fellow scholars, it gets worse. They found that the new method is indeed significantly better than the I have no idea baseline. This might sound crazy, but the authors of the paper also discuss this possibility. After all, if you look at the illustrations, they are exquisite works of art. Making similar quality drawings takes time. And the text takes up nearly twice as much space as the illustrations. Another paper from 2020 came to similar conclusions and also decoded some of the text. They found that some of the shapes correspond to astrological symbols and others to plants. So it may very well be that this is indeed an astrological or botanical book, but we don't know yet. So, who would spend so much time making drawings if the text is just gibberish? Here we see that the amazing illustrations that made this book famous are actually not helping us to decipher the text, at least not directly. But perhaps one day in the future, this paper will help us to see the book in a new light. What a time to be alive! Maybe the whole thing is a kind of diary of an insane person, but then again, maybe not. However, the bad news is that it is not significantly better than the older statistical method from 2009. And it is not significantly better than simply copying the training data. The authors of the paper propose a way to visualize what the neural network is thinking. They take the weights of the neural network and visualize them in a way that we can make sense of. And here comes the punchline. The resulting visualization makes perfect sense if we assume that the network is actually not looking at words, but at shapes. You see, if we remove the black bars, we get these colorful shapes. And these shapes appear to be localized around specific regions of the text. Remember that each input letter looks like this. So why would a neural network try to recognize shapes when given letters as input? Well, this is what neural networks do. They look for relevant features in the input data. For instance, if you have a handwritten digit recognizer, it will learn to recognize lines and curves and their arrangement and so on. These are the relevant features for recognizing digits. Here, however, these features happen to be localized around shapes. So that's what the neural network is seeing. Yes, you heard it right. It is not even significantly better than a neural net that has no idea what it's doing. And these tell us something interesting. They tell us which parts of the letters are relevant for distinguishing the different shapes. And this means that the neural network is actually doing something akin to template matching. Of course, this is not the usual way to think about neural networks, but that's exactly what this paper is about, finding out what a neural network actually does. In this case, they tried to decode a text with it. But it seems that instead of words, the neural network is looking for shapes. And this shape recognition works surprisingly well. What are we to make of this? Well, one explanation is that there simply isn't enough structure in the data to train a better model. However, I wouldn't bet on that. There is a much more interesting explanation for this. You see, the Google Translate neural machine translation system is trained on 800 gigabytes of data. This contains roughly 7,000 books. So while this is obviously much more data than 180,000 words, this is still roughly 1,000 times less data. This means that the neural network gets to see more than 1,000 times fewer examples of the Voynich text than of real books. Is this just a strange fictional language that the author made up? Or is there something else going on here? They took a recent neural machine translation system and fine-tuned it on a few dozen pages of the Voynich Manuscript. They were very careful to use proper baselines and error analysis. That means that they also have an older statistical method and a modern neural method that both don't see any of the training data. They only see the test set. They also compare it against various previous methods, and this is a super important part of the paper. They also compare it against a method that generates random text but still has the same distribution of n-grams. Basically, this is the I have no idea what I'm doing baseline. If the result is better than this, that's already a success. The book in question is this one. It is called the Voynich Manuscript, and it has remained a mystery for more than 100 years. Why? Because nobody knows what language it is written in. In his paper, he trained a simple statistical language model on the book. Such a language model works by looking at pairs of letters that appear next to each other and calculates how likely it is that they come together. If a bigram like th appears often together, then the model says that these two letters have a high probability of appearing next to each other. These building blocks can then be combined into bigger and bigger units and used to estimate how likely an entire sentence is. Now, if we were to train such a model on, say, Shakespeare, we would get a model that is able to generate a lot of Shakespearean English. The issue is now that while the basic building blocks of these models can appear pretty often in the Voynich text, higher-order statistics don't make sense. You see, these n-grams simply don't appear often enough to be able to train a proper language model. And yes, this also means that the famous n-gram model I talked about in episode 37 is too small to be able to make any predictions about this text. We don't know whether it contains a message or if it even has anything to do with language. But today a paper appeared that tries to crack the code with the help of modern neural networks. Does it work? Let's have a look together. The Voynich Manuscript was created around 1400 AD and is named after the bookseller Wilfrid Voynich, who purchased it in 1912. You see, when we zoom into the text a little, we see these strange swirls which do not resemble any writing system that we know. Even worse, if you were hoping to find some words that might look like Latin or Greek or maybe Sanskrit, you will be disappointed because words can be statistically shown to be of the same length throughout the whole book. And this length is also the same as the average word length of many human languages. This means that whoever wrote this book invented a writing system where the average word length is exactly the same as in real life. So why doesn't anyone understand it? In 2009, the computer scientist David J. Bogan wrote a paper where he looked at this problem from a statistical language modeling point of view. Now, this is already quite surprising because the book is only about 240 pages long, but it contains some 180,000 words. So much for background. Let's now have a look at the new paper. What did these fellow scholars do? So what did they find? First, the good news. It could be that this is not a text at all. It could be that it doesn't contain a message, and it certainly doesn't contain words. And all this brings us to the key idea of the paper. But wait, there are these black bars. And just for the record, this is not the only work with similar results. And thanks for watching and for your generous support. And I see you next time.